Okay, so these are the solutions to the linear transformation problem. The first section is asking us whether or not this is a linear transformation. The very first one is not, and we can just prove this. We can create two vectors, 1, 1, 1, and 1, 2, 1. Take the linear transformation of their sum. So this is going to be the linear transformation of 3, 2, which is going to come out as 3, 1. If I take the linear transformation of 1, 1 plus the linear transformation of 2, 1, I'm going to get 1, 1 plus 2, 1, which is going to give me 3, 2. Since these two are not equal, this means that this is not a linear transformation.
So when we look at this,
proving that one is a linear transformation takes a little bit more work. So let's create two vectors in R3. We'll call the one A, B, C. And we'll call the other one D, E, F. Alright, so these are both in R3. So the first thing is to take the linear transformation of each of them. And if I do that with ABC, I get A plus B, A minus B, C. If I take the linear transformation with D, E, F, I'm going to get D plus E, D minus E, F. We're also going to need a constant, so let's call P our constant. All right, so if I add these two, I'm going to get A plus B plus D plus E, A minus B plus D minus E, C plus F. Okay, so now I need to look at what happens if I take the sum of the two vectors on the inside. So this is going to be A plus D, B plus E, C plus F. Okay, so the first part says take A plus D and add that to B plus E. The second part says take A plus D and subtract B plus E. And the last part says just take C plus F. So it's not hard to see that by a little bit of rearranging here, we get the same result here as we do there. So the addition holds. Now we need to see if it works under scalar multiplication. So we take T of P times A, B, C, which is going to give me T of PA times PB or PC, which gives me PA minus P or plus PB, PA minus PB, PC. All right, so then I started on the other end and said P of P times A plus or ABC is P times A plus B, A minus B, C, which is P times A plus B, P times A minus B, B times C, which gives me PA plus PB, PA minus PB, BC, and this is the same as that. So this is a linear transformation. All right, so let's look at number 3. Problem 3. This is another one where we don't get a linear transformation, so let's use 1, 1, and 2, 2 as our counterexample. If I take t of 1, 1 here, I'm going to get 4, 1. If I take t of 2, 2 here, I get 5, 2. So if you add those, you get 1 plus 5, 2, which is 9, 3. If you take the transformation of the sums, you're taking t of 3, 3, which works out to be 6, 3. These are not equal, so this is not a linear transformation. Okay, so let's move on to number 4. Okay, so remember, you only need a single counterexample to disprove something. Number 4 is one of these cases. So let's use 2 vectors, 1, 1, and 4, 4. If you take the transformation of 1, 1, you get back 1, 1, 1. If you take the transformation of 4, 4, you get back 2, 16, 2. So the sum of the transformations becomes 3, 17, 3. But the transformation of the sums, which would be the transformation of 5, 5, is 5, 25, 35, which means these are not the same. So you do not have a linear transformation. All right, let's look at number 5. Okay, so remember, you can either disprove by using addition or you can disprove by scalar multiplication. So we're going to use the identity matrix here. If I take the determinant of the identity matrix, I get 1. Let's say I scale this by 2. So I'm going to take the determinant of 2002, which is 4. But if I take 2 times the determinant of the identity, then I'm left with 2. 2 does not equal 4. So the linear the transformation doesn't hold under scalar multiplication, so this is not a linear transformation. All right, so let's move on to number 6. 6 is going to be a linear transformation. Let's do this by letting C be this strange matrix. 0, 0, 1, 0, 1, 0, 1, 0, 0. This is the elementary matrix that swaps row 1 with row 3, so that's not so bad. We're going to let A and B be just 3 by 3 matrices, and we're going to let little b be a scalar. All right, so being able to shorthand this helps a lot. Let's take the linear transformation of A plus B. That means I take C times the matrix A plus B, which is C times the matrix A plus C times the matrix B, which is the linear transformation of A plus the linear transformation of B. This holds under addition. And then let's take T times the scalar times A. Well, that's going to be dA times, or C times dA, which is the same as D times CA, which is the same as D times the linear transformation of A, so that holds. All right, so this one is a linear transformation. It holds both under addition and scalar multiplication. Move on to number 7. All right, so number 7, let's let A be a 2 by 2 matrix. Let's let B also be a 2 by 2 matrix. And let's let C be some scalar, right? So if I take the transformation, or sorry, I let it as A1 and So A1 plus A2 is going to be A1 plus A2 times B, which is A1 times B plus A2 times B, which is the linear transformation of A1 plus the transformation of A2. So addition holds. Let's try it with scalar multiplication. This means I'm going to get CA1 times B, which is the same as CA1B, which is C times the transformation of A1. So we hold under scalar multiplication, which means this is a linear transformation. And we're going to look at problem 8. I'm going to play the same game I did in 7. I'm going to let A1 and A2 be matrices that are 2 by 2. C be a scalar. So T of A1 plus A2 is A1 plus A2 transpose, which is A1 transpose plus A2 transpose, A2 transpose, which is T of A1 plus T of A2. So the transpose here is working under addition. Let's see if it also works under scalar multiplication. So this is C times A1 transpose, which is C times A1 transpose, which is C times the transformation of A1. That works. So this one is a linear transformation. Let's look at number 9. In number 9, we have polynomials. So we have a polynomial a0 plus a1x plus a2x squared is a generic polynomial in P2. b0 plus b1x plus b2x squared is going to be a generic polynomial in P2. B is going to be a scalar. All right, so if I take the transformation of the sum, and so this is going to be the transformation of a0 plus b0 plus a1 plus b1 x plus a2 plus b2 x squared, which means that I'm left with a1 plus b1 plus 2 times a2 plus b2 x. If you're thinking about this, this is basically taking the derivative of a second degree polynomial. If I move things around a little bit, I'm going to get a1 plus 2a2 plus b1 plus 2b2. This is an x. This is an x, which means this is the transformation of a0 plus a1x plus a2x squared. And this is the same as b null plus b1x plus b2 squared. So that gives me closure under addition. Let's try it for scalar multiplication.
So go back to it.
So this is going to give me CA no plus CA1x plus CA2x squared, which becomes CA1 plus CA2 2CA2x, which is C times A1 plus 2A2x, which is C times A null plus A1x plus A2x squared. And we're good. So this one will also be is a linear transformation. So let's try number 10. Okay, so I made a bobble in my write-up of the solutions.
Our entire
If you
office
look,
hours has been.
what I just read is number 9 was actually number 10. I paused and I worked out number 9, and I'm going to present that here. And I will scan the solutions. So, all right. So in number 9, we got P of A0 plus A1x plus A2x squared, and then we're going to add to that another vector, B0, B1x plus B2x squared. Okay. So this thing says what I should end up with here, that this is the T of A0 plus B0 plus A1 plus B1 x plus A2 plus B2 x squared. So this becomes all of them added together, A0 plus B0 plus A1 plus B1 plus A2 plus B2 plus A1 plus A2 plus B1 plus A2 plus B2 x plus A1 plus or A2 plus B2 x squared. Right, so you can regroup a bit here. You can put all the A's together here.
So it might be just people trying to keep track.
And then you could put the A1 plus A2 x plus A2x squared plus all the b's
it wasn't working
plus
for her,
B1 plus B2x plus B2x squared, and that's going to give me T of A0 A1x plus A2x squared plus T of B0 plus B1x plus B2x squared.
Yeah.
All right, so then we got to do this. So that works. We have to do this with a scalar.
Yeah. Hey, Aubrey, come back. Yeah, like they seemed interested.
So that's CA0 plus A1x, CA2x squared, which gives me,
if I can remember how to do it again.
and then
you know how to do that? Crazy.
And then
that's too funny.
And quite literally can pull a C out of all of it.
Telling you, multi-talented. Where are you?
Which means that I now have
make you an admin.
C times
so that way you should have full range.
A0 plus A1x plus B2 x squared, and we have proven that this is an linear transformation. So there you go. Okay, so problem 11 turns the projection onto 1, 1 into a linear transformation. So part A says what happens if I do this with x, y. So I'm going to take x, y dot 1, 1 over 1, 1 dot 1, 1 times 1, 1. That becomes x plus y over 2 times 1, 1, which is going to be x plus y over 2, x plus y over 2. All right, so following along, that means that 5, 0 should be 5 plus 0, which is 5 over 2. 5 over 2. So let's keep going with this, and we'll look at part C. Takes a little bit more work. Part C is showing the addition part of the linear transformation. So let's do that next. So let's do this component-wise. Let U be the vector U1, U2. Let W be the vector W1, W2. So this means that T of U plus W is going to be U1 plus W1, U2 plus W2 dot 1, 1 over 2 times 1, 1, right? So that is the big sum, U1 plus W1 plus U2 plus W2 over 2 times 1, 1, right? Which just basically becomes U1 plus U2 over 2 times 1, 1 plus U2, sorry, W1 plus W2 over 2, 1, 1, which is the transform of U plus the transform of W. So we hold under addition. Part D asks us to see if it holds under scalar multiplication. So, alright, so let's do U as U1, U2 again. So we want to take C times the scalar of U, means that we got T of CU1, CU2, which is CU1 plus CU2 over 2 times 1, isn't C times U1 plus U2 over 2 times 1, 1, which is the same as C times CU. And that proves it for scalar multiplication. And then we have a composition of TLC for part E.
I can still see and hear you.
So this means we have 3 plus 4 is 7 over 2 times 1, 1, which means I'm taking C of 7 halves, 7 halves, which is 14 over 2 over 2 times 1, 1, which is going to be 7 over 4, sorry, 14 over 4 times 1, 1, which is 7 over 2 times 1, 1, which is 7 halves, 7 halves. All right, so that's the entire problem set. Sorry about the glitch on number 9 and 10 there. And again, if you have questions, make sure you stop in the drop-in or you email me, and I think we should be good. Thank you.